Had to stop the recording there. The nurses came in for a moment, so here's part two. When we left off, we were looking at linear loads. Here's a quick example where we have a beam with two triangular loads on it. This one reaching a max of 50 pounds per foot, this one reaching a max of 50 pounds per foot, but they're kind of in opposite directions. But no matter, that's perfectly fine. Let's think about making this beam and creating an equivalent beam with this by replacing the distributed loads. Okay, so here's our wall, our beam coming out. And let's look at these two distributions separately. All right, this first one here reaches a maximum of 50 pounds per foot, and it acts over 9 feet. So the location, if we sort of split this beam in half, we're looking at sort of the first location now. We know that we're going to put our equivalent force 1/3 away from the larger portion of the distribution. So here is our equivalent force for the first portion. It's going to be 1/2 base times height. So 1/2, our base is 9 feet, times height, which is reaching a maximum here. The maximum is actually given here of 50 pounds per foot. And so that's going to give me 225 pounds. So that's that. And let's be clear about our location. Our location is going to be 2/3 of the way from the left-hand side. So this is actually going to be at a location of 6 feet. Okay, pretty straight ahead. We're going to do the same thing with the other distribution here. So here we have another triangular distribution. This one isn't really starting at b equals 0, but we do have kind of this right-hand side where it does get to 0. So I think because it has this triangular shape and not a trapezoidal shape, we can go about analyzing it with our typical methodology. So our centroid again is going to be 1/3 of the way from the larger side. So our centroid is going to be here. We're going to have some equivalent force acting upward. So here's our equivalent force number 2. And this is going to, again, be 1/2 base times height. So the base, 9 feet. The maximum height is 50 pounds per foot. So similar idea. We're going to, again, have an equivalent load of 225 pounds. And this is going to be located 1/3 of the way past the large portion. So if we want to measure kind of from the left-hand side, which I think might be helpful here, it's going to be this distance is 9 feet, and then we're going to add an additional 3. So it's going to be 12 total from the left. And there you go. That's the location of our equivalent force. I drew this a little bit misleading. There you go. Okay, so that's linear distribution. Starting at 0. I think it's at this point where we sort of stop with kind of the standard distributions and what they look like. Triangle, rectangle, all good. Now you might see some more crazy type distributions, and I'll just pop in one of the lecture slides here and talk about centroids and areas of common shapes that you might have for some distribution. So I'm going to share this on my screen here now. We see centroids and areas of common shapes. We've already seen the rectangular area here. So we looked at that already, a distribution that has a common or constant loading function, W equals C. That's pretty straight ahead. We're going to locate the centroid of this as b on 2. Pretty simple. The area is base times height. All right, for a triangle, the centroid is 2/3 of the way towards the larger half. If it's a non-right triangle, then this x-bar location is a plus b on 3, where a is the distance to the peak and b is the total base. So that gives you a general idea there. The area is 1/2 base times height, no problem. We have other ideas of centroidal locations and areas for, let's say, a semicircular area, quarter circle area. These might occur in practice. These are common for modeling of let's say tires touching the ground, right, where you have a contact point, or maybe some elliptical distribution, some parabolic distribution. Here you go. If those ever come up, you have a reference here in the slides to take a look at some of these other different types of areas. Let's go on and look at an example that kind of utilizes this conversion of distributed loads into point loads. I'm going to pop this into the slides here really quick. This is the example from page 8 on the deck. We have this distribution here, and I'll bring the prompt in here as well. Oh, all right. So here we have this beam loaded with the distribution shown. We want to create a free body diagram of this beam by replacing the distributed loads with equivalent point loads. Then we'll determine the reaction forces at points A and B. All right. So I think we can go ahead and identify that we have two pretty common distributions. One is this rectangle shown here, which is a constant loading function. And here we have a linear distribution, which is here. We have a maximum value of 150 pounds per foot on this constant load. So I think pretty straight ahead, we can go and take a look at this. And so here's an equivalent beam. We're going to see two different distributions. Maybe we call this distribution number 1, distribution number 2, which we're going to replace. Let's put some dimensionality in here. Okay. I'm going to replace the triangular distribution with an equivalent force that's 1/2 base times height. So here's FEQ for region number 1. This is 1/2 base, which is 6 feet, times height, which is 150 pounds per foot. Okay, so this is going to give me 450 pounds. And I'm locating this 2/3 of the way from the left-hand side, so this is going to be at 4 feet. Okay, pretty straight ahead. Let's do distribution number 2. Here I have a rectangular distribution, so I'm going to locate it at the center of this rectangle, which is 6 plus 4 feet from the left-hand side. So it's going to be generally in this location. And here's FEQ number 2, which is base times height since we have a rectangle. So 8 feet times 150 pounds per foot. This is going to give me 1,200 pounds. And we're locating this. You can either think about doing it from the right or from the left. I like going from the left, starting everything at like the 0 location. And this is going to be 10 feet from the left, because it is this 6 feet plus half of the 8 feet. All right. So that's kind of our equivalent beam. We still have our roller here at A. We still have our pin here at B. I'm just creating for myself an equivalent beam at this moment. Once I have this, now I can start actually doing the free body diagram. That includes information about what's happening at the reaction at A and the reaction at B. Okay. So let's get this fully in here now. At A, we have a roller. At B, we have a pin. And we have our equivalent force. I'm just going to draw this in here, remind you what that is. In location 1, it's 450 pounds, 4 feet from the left. And for the rectangular distribution, we have over here was 1,200 pounds. And this is 10 feet from the left. Okay. So this is the situation that we currently have. The beam has a total length of 14 feet, if that's important. So that's going all the way out to the left there. All right, we're ready for equilibrium. We can sum the forces in X equal to 0. That's going to pretty easily lead us to FBX equals 0. We're going to sum the forces Y equals 0. We have FAY plus FBY. Minus 450 minus 1200 is minus 1650 equals 0. We can't really solve for anything in this general setup. So FAY, FBY are two unknowns, so we're going to have to go to a summation of the moments. Let's sum the moments, let's say about A equal to 0. 450 is going to contribute, 1200 is going to contribute, and FBY will contribute. So we're going to get a negative 4 feet times 450 minus 10 feet times 1200 pounds. And then we're going to have FBY, and this is at 14 feet. Equal to 0. I don't have my calculator here with me. You could solve this for FBY. Solve for FBY, no problem. Once you have FBY, you can solve for FAY. And we're done. So that's that particular example. All right. Last thing to discuss before we close out this lecture is what to do with more complicated loading situations. And what I mean by more complicated loading situations is actually something we will call compound loading situations. So let's look at compound loading functions. All right. So some loading functions that you see can actually be broken down into more simplistic loading structures that we've already talked about. So some complex loads, distributed loads that is, can be broken up into more simplistic distributions. And the classic example of this is the trapezoidal loading function. So this is a linear type of loading function that does not start at a 0 value. So there's an example in the lecture deck here. I'll just take this one directly. Looks a bit like this. So here we have this trapezoidal loading function. It's a linear distribution which does not start at 0 or does not end at 0. So it has this trapezoidal shape. And, you know, remembering what is the area of a trapezoid and what's the centroidal location of a trapezoid is actually kind of difficult. So instead, what you might want to do is break this up into a compound loading function where you have two different distributions. One which is a rectangular distribution with a magnitude of 50 pounds per foot, and one which is a triangular distribution here. So maybe you call this loading function number 1, and you call the rectangular loading distribution number 2. So this trapezoidal loading then can be thought of as a combination of the triangular plus rectangular. And this example, you sort of see that happening. Loading distribution number 1, we have the centroid 1/3 of the way from the larger side. So here might be your equivalent load. And the rectangular, your centroid of the rectangle is going to be right directly in the center. So here's the equivalent load associated with the rectangle. And we see that here, F1 for the triangular and F2 for the rectangular. All right, so pretty straight ahead, just breaking down what looks like kind of complicated distribution, a trapezoidal in this case, into two simplistic distributions, a triangular plus a rectangular. We'll do one quick example here, and then we will call the lecture. This is the last slide of the lecture deck, and it is this example here. I'll just copy and paste it best I can. So here's the prompt, and I'll get the picture in here. Okay, put it all the way down there. Bring that back up. Okay, here we go. Beam is loaded with compound distribution as shown. Create a free body diagram, replace the distributed loads with the equivalent loads, and calculate the reactions at A and B. So let's go ahead and do our equivalent loads. Okay. And this first load that we see here on the right-hand side is kind of a trapezoidal distribution or trapezoidal looking function. And our second is a rectangular. Rectangular, we can handle, we can deal with, that's no problem. Trapezoidal, we have to use kind of these compound loading function situations to deal with. So I'm going to break this trapezoidal into a rectangular and a triangular distribution. And we can sort of label these as, maybe I label this distribution as distribution number 1. This distribution is distribution number 2. So 1 is the triangle, 2 is the rectangle. And then this last one here, we'll label as number 3. Let's keep our pin and our roller in here. So here we still have our pin at A, we have our roller at B. And let's look at our various equivalent loadings. All right, so here we have somewhere over here, F equivalent for loading distribution number 1. Here we're going to have something for F equivalent number 2. And over for the third distribution, I'm going to have an equivalent loading number 3. I'm not going to try to fit all of these onto this figure. Instead, I'll just sort of write them down below. So FEQ number 1. This is the triangular distribution, and we have to be a bit careful here. The area of this guy is 1/2 base times height. 1/2 the base, I think, is pretty clear to understand, 4.5 meters. But the height, you want to make sure you're only taking the height of the triangular distribution. So the height of the triangle alone is the total height here, 6. That's this height of 6 minus the portion on the bottom we're gonna subtract. So this is 6 minus 3 is actually this total height. Let's make that a little bit more clear. So if I'm looking at the triangle alone, this is 6 minus 3, this height here. Right? So we have this is 6 minus 3 kilonewtons per meter. So in total, this is 4.5 times 6 minus 3, or 4.5 times 3. It's 13.5 divided by 2 is going to be 6.75 kilonewtons. This is located 1/3 of the way from the larger side. So it's 1/3 of 4.5 meters. So this is located at a position of 1.5 meters. Let's look at our equivalent force number 2. This is for the rectangular distribution. So it's going to be base times height, 4.5 meters, times the height here of the rectangle only is 3 kilonewtons per meter. So this gives me 13.5 kilonewtons. And this is going to be located at X bar 2 position, which is halfway along the length of the rectangular portion, so 2.25. meters from the left-hand side. Lastly, We're looking at our third portion of the distribution, which is a small rectangle on the right-hand side. This guy has a height of 3 kilonewtons per meter, and it has a width of 1.5 meters. So 3 times 1.5. And we get 4.5 kilonewtons. And this is located at position 3, which I'm going to measure this kind of from the far left-hand side. Notice I'm kind of taking everything from the left. So this is X bar in position 3. So it's going to be this 4.5 plus half of 1.5. Okay, so 4.5 plus 0.75, it's going to be 5.25 meters. So this is the full setup for replacing your distributed loads with individual point loads. And let's go ahead and sketch the free body diagram now. Okay. Point A, we had a pin. That's the far left-hand side over here. It's this pin. So we know we get 2 forces at a pin. Point B, this is an overhanging beam. So point B is there, and that's 4.5 meters from the left. So here's FBY. It's 4.5 meters from the left. And let's start putting our equivalent forces in. The first equivalent force is from the triangular load. Scroll up here. That's this guy, 6.75 kilonewtons, and that's 1.5 meters from the left. The second equivalent load, this is from the larger rectangle. So that's this guy here. And that's going to be 13.5 kilonewtons at 2.25 meters from the left. And the last one we have is the far right-hand side. That's another rectangular distribution, 4.5 kilonewtons at 5.25 from the left. Okay, so that's it. I'm going to call the example here. We kind of have simple 2D equilibrium at this point with a beam. Everything's kind of at nice right angles. You could go through this and solve FAY, FBY, and FAX pretty simplistically. That's it for distributed loads. We'll consider this slide deck closed. Hopefully I'll be back on Wednesday, and we'll dive into the next set of lecture notes then. See you then.